Okay, let's talk about reactions of alkenes. Um, when you're taking an organic chemistry class, generally, most courses will study reactions one functional group at a time. Um, and so we're going to start with alkenes. And when you consider a new functional group and think about how they might react, you want to think about those frontier molecular orbitals. Um, if you happen to skip Module 10 and you're studying these reactions, but you don't know what molecular orbitals are, that's okay. You can kind of jump ahead past this part. You're going to need to understand these reactions in terms of the curved arrows, but not necessarily the molecular orbitals. Um, but if you did do Module 10, then you should be able to identify the HOMO and the LUMO of a typical alkene, and we're going to draw them. So the HOMO of an alkene is going to be pi cc, and the pi cc orbital is going to be made of a p orbital on each atom overlapping with each other. So you end up with what looks like a hamburger bun shaded on one side, not shaded on the other. Uh, so that's going to be the orbital when an alkene is donating electrons. That's where those electrons are going to come from. And then the LUMO would be pi star Cc. And remember, pi star orbital is going to look sort of like a clover leaf, but separated. And since these are both carbon atoms, it's going to be symmetrical. And even if I didn't draw it perfectly, those lobes should be the same size on both carbon atoms. Um, So if these are going to accept electrons, those would go into pi cc. Now, pi cc is a decent donor. We're going to see lots of reactions where pi cc acts as the donor. Pi star cc is not a good acceptor. We're not going to see reactions where a nucleophile donates directly into pi star cc. The one kind of reaction we will see is when we have pi cc donating into some other orbital, we might see pi cc act as an acceptor at the same time, but never pi star cc acting as an acceptor on its own. Okay. One thing that uh, you might recall if you did module 7 is that these things can't rotate freely. And the reason is when we have that pi bond, we have overlap between our two p orbitals on the two carbons to make that pi bond. If we tried to rotate around the bond, then we would have to go through, let's say I'm rotating that carbon on the right, so now the carbon on the right is planar and those substituents are in the plane of the page. Now I would have a situation where I have one p orbital on the left that's in the plane of the page, and the other p orbital would be coming into and out of the page. And when we get to that point, essentially there is no overlap. These two orbitals are perpendicular. So no overlap. And when we have orbitals that don't overlap, that means the bond has to be broken. Bonds don't want to break. So you would need to put in a lot of energy to make this happen. And therefore, this just doesn't happen without a whole lot of energy. So the bottom line is no, they cannot. And in Module 7, we looked at the implications of that, and that's why we get E and Z alkenes as isomers. So that's just a reminder. Let's look at the typical type of reaction for alkenes, and that's going to be the focus of this module. All right. So we've already said that for an alkene, the HOMO is pi Cc, the LUMO is pi star Cc. A typical reaction partner might be something like HBr or HCl or HI. The thing you might remember about these is this is a strong acid, meaning it tends to dissociate and give up H+. The HOMO for this molecule is going to be the lone pair on bromine, and the LUMO is going to be sigma star HBr. Now, when you consider these orbitals and you're thinking about what might donate to what, it might be a little hard for you to determine which is going to be the better interaction. But I've already told you that pi star Cc is not going to act as an acceptor very often. So the interaction we're really going to be looking at is between pi Cc and sigma star HBr. Meaning, I'm going to start my arrow at the pi bond between the two carbons, and I need to attack the HBr antibonding orbital. Now I know that based on polarity, hydrogen is partially positive and bromine is partially negative. So if I'm a pair of electrons, like that pi Cc pair of electrons, I'm going to want to attack the positive side of that bond. So I'm going to attack the hydrogen. And when I do that, I'm going to break the HBr bond. Now, when I do this, I'm going to draw in the existing hydrogens, and I'm now bonding to a new hydrogen. I'll highlight that in purple. I have a choice now. I can put that new hydrogen on the left side or the right side. In this case, my alkene's symmetric, so it doesn't really matter. So I'm going to arbitrarily choose the left side. And if I do that, notice now my carbon on the right only has 3 bonds, and it doesn't have any other pair of electrons. So that's going to be a carbocation. So you just did a module all about carbocations. We said this was one way you could form carbocations. So here's our example in action. Now, carbocation we know is very high energy, very unstable. It's really screaming for electrons. And the thing about a carbocation that I want you to know is it will fall in love with the first nucleophile that it meets. It will bond with whatever is around that has electrons. So in this case, the other nucleophile that I have around is going to be my Br minus ion that was generated in that first step. And so it's not hard to predict that that will go and bond to my carbocation. And what I'm going to form is an alkyl halide. So this is a transformation of an alkene into an alkyl halide. So the way we would write this, in general, if we're just talking about our functional groups, we would say an alkene reacts with HBr, or to make it more general, I'm going to call it HX, where X is Cl, Br, or I. and we make an alkyl halide. The way we would write this specific reaction above would be to write my reactant on the left, have my reagent over the arrow, and then my product on the right. And then I was kind of silly. I jumped the gun on my general description and put it where I didn't intend to. So that belongs down here where this is how we would describe the reaction in general. All right, so this is the first organic reaction that you're required to memorize. You should know the starting material, the reagent, the product, and how we get there. So turning an alkene into an alkyl halide, relatively simple. We're reacting with a strong acid, HX. Notice this was the simplest case we could have because this was a symmetric alkene. If I were to do this with an asymmetric alkene, it brings up other considerations. So that's what we'll look at next. All right, let's go ahead and consider the case where we have an asymmetric alkene. All right, so here's an example of an asymmetric alkene where I have my double bond between two carbons that have a different number of substituents. We would call these the more substituted carbon and the less substituted carbon. More substituted means it's bonded to more other carbons. Less substituted, it's bonded to fewer other carbons. So just to give that terminology, this is more substituted on this side, and this would be less substituted. Now, when we're doing this reaction, and I'm going to have PiCC attack my acidic hydrogen again, notice now I have two choices. Okay, I can leave the carbocation on the more substituted carbon, or I could leave the carbocation on the less substituted carbon. If I leave the carbocation on the more substituted carbon, it would look like this. If I put it on the less substituted carbon, it would look like that. And notice I could take either of those carbocations, and I know that they are going to react with the first nucleophile they see, which in this case will be bromide. And those two pathways give me two different products. All right. So the question is, which of these two products would I actually observe? Do I get a mixture of both? Do I only get one? And it turns out that I do only get one. I don't actually get the product on the right. This is the observed product. So we call this kind of reaction regioselective. There were two regions where the bromine could have bonded. It only bonded to one, so I selected between the two. Generally, when we're trying to explain regioselectivity, there are two possibilities that we consider, two broad categories. One would be a kinetic explanation. And in a kinetic explanation, what we're saying is one product is formed much faster. Now, if you remember from general chemistry, the reason one reaction might happen faster than another is because that pathway has a lower activation energy. We could also offer a thermodynamic explanation. In a thermodynamic explanation, what we're saying is, no, it's not necessarily the speed of the reaction. And often when we're using a thermodynamic explanation, we have a reaction that actually can go back and forth and will eventually settle on the more stable product. So a thermodynamic explanation is that one product is much more stable than the other. So when the mixture reaches equilibrium, there's more of that product. Okay, so let's ask ourselves which of these two makes sense. And now you have the advantage of having done Module 15 about carbocations, so your instincts might already be leading you in one direction. Now, both of our potential explanations involve energy. And so it can be helpful to put our thoughts down in diagrams. And this is one of those overlaps between biology, you'll see these diagrams in biology, general chemistry, and organic chemistry. So to think about that, let's draw ourselves what we call an energy profile for this reaction. Remember, energy profiles are these diagrams where you have energy on the y-axis, you have reaction progress on the x-axis, and you're saying as the reaction occurs, this is what happens in terms of energy. Generally, they look like this. They've got a hill in the middle, and then they've got the reactants and products on the two ends. So when we think about this addition of HX, we know that this carbocation is a very high energy intermediate. What that means is in this reaction, we are going to have a first step with a high hill, and the intermediate, I'm going to redraw this so it's right under the carbocation. The intermediate carbocation is going to be very close to the top of that reaction hill. Okay, so my carbocation lies right here. And then after we form the carbocation, there's not going to be much of an activation energy for the bromide to bond to it. So the second hill should be short, and my product, turns out in this case, is lower in energy than where I started. So if we think about this reaction, the first step is what we call the rate limiting step. And my activation energy for this reaction would be the difference from the reactants up to this transition state, which is close in energy to that carbocation intermediate. And because that first step has such a high hill, that's going to determine how quickly this reaction can happen. So based on that argument, it's not a big logical leap to imagine that the energy of the carbocation is going to play an important role here. If the carbocation is super high in energy, that hill is going to be super tall and really slow this reaction down because you may remember from general chemistry, only reactants that collide with enough energy to get all the way up that hill will actually successfully complete the reaction. And the higher that hill, the more unsuccessful collisions there will be. between reactant molecules. All right, so in general, this is what our reaction energy profile is going to look like for addition of HX to an alkene. Big, tall hill for the first step, shorter hill for the second step. Now, this slide you've already seen in Module 15. Just as a reminder, a primary carbocation or a methyl carbocation is so unstable that it will pretty much never form. As we add substituents, our carbocations get somewhat less unstable. To the point where a tertiary carbocation is still unstable, but not ridiculously so. So remember, we would call this primary, secondary, and tertiary. Remember, we explained that by hyperconjugation. And that was the donation from neighboring sigma bonds stabilizes the carbocation. And as we move to the right in this chart, we had increasing hyperconjugation. So if I consider the energy profile for my two potential pathways here, I have one pathway that's going through a primary carbocation, and I have one pathway that's going through a tertiary carbocation. Now, both of these are going to be unstable. They're both high energy intermediates, but the primary carbocation is much higher in energy. Therefore, when I consider the activation energy to form the tertiary carbocation is going to be much smaller and therefore that hill is a lot shorter. Okay, the two products in this case, it turns out, have very similar stability. The more substituted alkyl halide is somewhat more stable, but only by a little bit. But the difference in energy of the carbocations is huge. So because of the smaller activation energy to form the tertiary carbocation, that step is going to be millions of times faster than the step that would form the primary carbocation. So in this case, the kinetic argument is the one that really explains the difference. This primary product is just formed millions of times more slowly. And that's why we just don't observe it. And I'm saying millions there, not precisely, just many orders of magnitude slower. The pathway that goes through the tertiary carbocation, lower activation energy, proceeds faster. In general, we're going to see a pattern. This was first noticed before an explanation was developed. It was noticed by a chemist named Markovnikov, um, and his name has been attached to it ever since. And he noticed a pattern in reactions, and that was when a polar reagent, so a polar reagent meaning something with a partial positive and partial negative end. So, for example, HBr, where I had a partial positive and a partial negative. We'll also see reagents like water being added, where there's a partial positive and a partial negative. We'll see others as well. But when a polar reagent is added to an alkene, the partial positive side, which is usually hydrogen, bonds to the less substituted carbon, and the partial negative side bonds to the more substituted carbon. All right. We will see that pattern in most of these reactions. And most of the time, we can explain it using just our principles of reaction mechanisms, like we just did. Okay. But when we say this is a Markovnikov addition, that's what it means. It means the hydrogen bonds to the less substituted carbon, the more electronegative atom bonds to the more substituted carbon. All right, so that's our first example of an addition reaction to an alkene. We'll see a couple more examples coming up.